Hi, everybody. I want to talk to you today. Basically, just reviewing a little bit of the chemistry because it's been a little while. So, if you'll bear with me, I will share my screen and we'll get started. Okay, so we'll start off with matter. Matter is anything that takes up space and has mass. Rocks, metal, oils, gases. Yes, think about that for a minute. The air that is surrounding us, the air that you are breathing, is matter. So it has mass and it takes up space. Think about how could you test that idea? And I say think about it because you may be asked to do that. An element is a substance that cannot be broken down into other substances by chemical reactions. We know of 92 elements that occur in nature, although obviously, if you look at the periodic table, there's more than 92. It's just they're not all naturally occurring. A compound is a substance consisting of two or more different elements combined in a fixed ratio. So like H2O, we have hydrogen, we have oxygen. We know there's two hydrogens, one oxygen. It's always in this specific ratio or combination. NaCl, which is sodium chloride. Sodium is Na, chloride is Cl. Now this brings around a little twist because when you talk about molecules versus compounds, a molecule is two or more elements combined. A compound is two or more different elements. So all compounds would be molecules, but not all molecules are compounds. For example, O2, that's one we're going to deal with a lot. Oxygen gets lonely. Oxygen doesn't like to be by itself. So you're always going to see oxygen bound with something. If it doesn't have anybody else to be friends with, it'll be friends with another oxygen. So O2 is a molecule, but it's not a compound because it's both the same type of element. Okay. So that's something you need to make sure you're straight on. Compound versus molecule. So when we talk about essential elements, of the 92 naturally occurring elements, we say 20 to 25% of them are actually essential to survive and reproduce. The four key ones that make up 96% of all living matter is what we call CHON: carbon, hydrogen, oxygen, and nitrogen. Now, as we move through the year, you're going to see this abbreviation, but you're also going to see one more added sometimes, a P for phosphorus. It's also one of the biggies when it comes to living organisms, but it doesn't fall into that 96%. And then we have trace elements. Of those 92 naturally occurring elements, these are going to be required by organisms, but they're really in very, very small quantities. So they're not going to be the biggies. Okay, so hopefully you all recognize this. It's a kind of a view of part of a periodic table. Okay. So we start when we're looking at a block on the periodic table with the idea of an abbreviation, because a lot of times, sometimes we don't want to write the whole word on there. So you'll see an abbreviation. It's always typically a two-letter word. If it's one of the ones that says three letters like UNN, those are some of the ones that actually are unnamed. So element, symbol, and if it and it will be a capital and then lowercase. If you see two capitals side by side, we're talking about two totally different elements. We have a small whole number, the atomic number. This specifies the number of protons that the element has. In a neutral element, it would also tell you how many electrons there are, but most of the time the electrons are going to change. They may be shared, or they may be donated to another atom, or they may pick up extra electrons. So we can't be 100% about the electrons based on the atomic number, but we know that that's the number of protons always. And then we have a decimal number that's the atomic mass. It's the number of protons plus neutrons averaged over all the isotopes. So we might have a helium-4, we might have a helium-2, we might have, and so we can get some variations if we checked every single atom. And so what they did is they averaged them all together, and that's where we got the average number, which is what the atomic mass you'll find on the periodic table is. So elements that are in the same vertical column, that's up and down, have the same number of valence electrons. So everybody in this very, very first group, and notice that first vertical column, the columns we call groups. So everybody in that first group is going to have 1 valence electron. Everybody in the second group has 2 valence electrons. Now it gets a little weird because these ones that are in the middle, we kind of ignore because they have some variation in them. We jump way over here. So group 13 would be our 3 electrons, 14 is 4 electrons, 15 is 5 electrons, and so forth all the way over. Okay, so groups give us our valence electrons for the main rows, but remember 3 through 12 are going to have their own little requirements. The rows across are what we call a period. So elements in the same horizontal row have the same total number of electron shells. So if you are in period 1, you're going to have 1 electron shell. In period 2, they're going to have 2 electron shells, and so forth along the way. So we're going to find consistency across the rows, and we have consistencies in the columns. So we're going to talk about the Bohr model. If you remember from your chemistry, what you found was that there's multiple models. We have Bohr models. There's some that have different valence shapes based on the different shells, you know, and you get barbells and you get X's and you get all sorts of different shapes. And then we talk about the electron cloud. And they're all general ideas about where we're going to find the electrons. But we tend to use the Bohr model a lot of times because it gives us more of a structured valence electron concept. So the Bohr model shows electrons orbiting the nucleus of an atom, and the electrons are going to be placed on shells around the nucleus. Each shell is what we call a different energy level, and so it can hold up to a certain number of electrons. The first shell can only ever hold 2. Second shell can hold 8. The third shell can hold 18, but remember only 8 of those would be considered valence electrons. So lithium, which is in group 1, period 2, it has an atomic number of 3, and 3 tells us protons, but it also hints at the electrons. So we say it's 3 protons. To be neutral, it's going to have 3 electrons. So we're going to have our first valence level, first shell, holds 2, and then on our second one, we get 1. And then we have the Lewis dot model. This one's pretty straightforward. All it's about is telling you about the valence electrons. So it's what we call a simplified Bohr diagram because it doesn't show all the different energy levels. What it tells us is those valence electrons. So it's only going to show the electrons in the valence shell, that outermost shell. Electrons are going to be placed around the element symbol. So if we were talking about carbon, we'd write a C and then we'd put the dots around the C to show the valence electrons. So using the same example we used on the previous slide for the Bohr model, we're going to talk about lithium again. And lithium in group 1, period 2, has 3 electrons. So we would write the symbol Li with 1 dot to represent that 1 valence electron, because the first 2 were in the other level and they're not valence. Elements want to be stable. Everything that these things do is because they want to be stable. So how does an element achieve this? Atoms that have incomplete valence shells will interact. So this lithium only has 1 electron and it wants either none or 8 in this level. So it's going to interact with other elements to form chemical bonds. Chemical bonds are an attraction between 2 atoms resulting from the sharing or transfer of valence electrons. And so a lot of times we use a concept called electronegativity, which is the measure of an atom's ability to attract electrons to itself, to kind of determine how reactive something is. And so we find that typically as we move across the periodic table from group 1 to group 18, the electronegativity will increase. And as we move down from period 1, moving down the periodic table, we find electronegativity typically decreases. These are just general trends. So when we talk about them interacting, typically what we're saying is they're bonding. And so we have different types of bonds that we focus on. We find with a lot of our main biological molecules, we deal with covalent bonds, and then some of the smaller molecules, things that we often refer to as like electrolytes, we're going to deal with other types of bonds. So covalent bonds are where we share electrons between 2 atoms or more. So they're going to form molecules, they're going to form compounds. Remember we talked about how O2 would be a molecule, but not a compound. H2O is both a molecule and a compound. They're both a combination, but one's with just one type of element, the other has 2 different elements. But both of those use covalent bonds. So we can have a single bond where 1 pair of electrons is shared. So the electrons go hanging around one of the elements and then they go hang around the other, back and forth. And it's almost like you could think of them walking in a figure 8. We can have double bonds where we have 2 pairs of shared electrons. So it's almost like we have 2 figure 8s going on. We can have triple bonds with 3 pairs. And when we divide up, we can take these covalent bonds and we can split them into nonpolar covalent, where the electrons are shared equally. So they make a loop around one, they make a loop around the other, make a loop around one and the other, back and forth. O2 is a very good example of a nonpolar covalent. The electrons are going to share back and forth around each of them equally. So they're both happy. Nobody's getting more attention than the other. This has double bond, 2 pairs shared electrons, and you can see how we've shown it with the Lewis dot structure. Then we have polar covalent. The electrons are not shared equally between the 2 atoms. Water is probably one of the most commonly discussed and most commonly used polar covalent substances. We often call it our Mickey Mouse molecule because we have his head and we have his two little ears for the hydrogens. So the oxygen is a little bit stronger. It's more electronegative. The hydrogens are weaker. And so what happens is they don't share equally. Those extra electrons tend to hang out with the oxygen more than they do the hydrogen. The oxygen's like the big party guy everybody wants to hang around, and the hydrogens, they're like, you know, he's okay, he can come visit, but we'd much rather hang out with the party guy. Okay, so what happens if we've got more electrons hanging around the oxygen, it tends to get a slightly negative charge because electrons are negative, and because they're not hanging around the hydrogen very much, we get slight positive charges. And they act, and the chemistry teachers always get mad at me when I say this, but it makes sense to me and most of my students. They kind of act like little magnets. So that slight negative charge can actually be attracted to the slight positive charge of another water molecule or some other molecule. And so it makes actually a stronger bond situation because it has a little extra pull with these minor charges. Then we have ionic bonds. So this is going to be an attraction between what we call oppositely charged atoms. So where we got those little teeny tiny bits of charges with the polar covalent, this is totally different. We're talking, these are major charges because this is all about give and take. If someone gives you their pencil, you will take it from them. There is a physical exchange. So this is what forms our ionic compounds and our salts. For example, sodium chloride, that's one of the most commonly demonstrated and modeled, and it's actually important in the human body, compounds, sodium chloride. Lithium fluoride is another big ionic compound. The idea here is that we're going to transfer an electron from one atom to another atom. So in sodium chloride, we're going to take the extra valence electron off of sodium and we're going to stick it on chlorine, which wants an extra electron. So we're literally moving the charge from sodium to chlorine. This leaves us with a cation, positively charged ion. I remember I like cats. And so because I like cats, that's positive. So I know it's the charge that's positive. Well, if you give away an electron, you have more pluses than minuses. Sodium's going to be positive. Anion is negatively charged ion. Normally, as long as I can remember the cation, then I know anion's the other, but anytime you put an A in front, that often makes it a negative or an opposite. And so chlorine would be our anion. We call it chloride at that point. And then there is an attraction between the anion and cation to form the bond. So that plus and that minus attract each other and stick together, like if we took a positive and a negative magnet and stuck them together, or north and south if you're thinking of the magnets that way. So sodium has one, chlorine is missing one to be full, to be stable. So the sodium gives their valence electron to chlorine. So sodium's now a cation, positively charged. Chlorine is now an anion, negatively charged, and we call it chloride, sodium chloride. And then that plus and minus hold them together. Another big type of bonding that we deal with a lot in this class is what we call hydrogen bonding. And hydrogen bonds are what we would consider a weak bond. When we say they're a weak bond, they're easier to break. And so compared to covalent and ionic, hydrogen bonds are weak bonds. They're easier for us to break them apart and put them back together. And that's really important in terms of functioning in a lot of places that we find hydrogen bonds. So the partially positive hydrogen atoms in one polar covalent molecule will be attracted to an electronegative atom in another polar covalent molecule. So the idea is we're getting that slight attraction between a little bit of positive and the little bit of negative. And this is what we would consider an intermolecule bond. So we're actually forming bonds between two different molecules. Covalent and ionic, this is how we're actually forming molecules and compounds. Hydrogen bonding is going to be between two different molecules, intermolecular. So why would this happen? When a hydrogen atom is bonded to an electronegative atom, a lot of times it's usually oxygen, nitrogen, or fluorine. Those are three of the most common. The electrons are not being shared equally. So we've got that polar covalent bond idea where they hang around one of the elements more than they do the other. One's more popular than the other. So this causes the hydrogen to have a partially positive charge and makes it possible for that electronegative atom to have a partially negative charge. So that oxygen or nitrogen or fluorine or some other. So when we're talking about hydrogen bonding, right? Here we're showing it with water. So we're doing hydrogen bonding between water molecules. So remember, oxygen's more popular, so it's going to have that slight negative. The hydrogens are more positive because they're not as popular. So the positive of this hydrogen will be attracted to the negative of the oxygen from another water molecule. And so we form these weak hydrogen bonds between these molecules. Water molecules move around a lot. Think about, you've got a glass of water and you're twisting and turning it and the water's moving. So these hydrogen bonds are forming and breaking and reforming quickly and easily. The hydrogen bonds between water is what make it more structured than most liquids. It actually helps it hold together. And we'll do some experiments and things dealing with that a little later after we talk more about water. Okay, so hopefully this helps you review a few of the chemistry concepts and you have a better recollection of all of the information. See you next time.